Alrighty, everyone. Hello and welcome back. Now we are finishing up, or this is going to be the second half of the. Not even sure what lesson we're on at this point in time. Lesson 6, I believe we are. Yeah, dealing with Poisson regression. All right. So last time we left off talking about the Wald test. So once we've created our model and we've interpreted what the coefficients mean, and remember, we do this differently than what we did beforehand, because what we did beforehand, we had a model that had a natural link function to it, which was the identity function, which means we didn't need to change anything. So when we saw an increase in one variable, well, how did it change the response or the predicted of the response? Well, it was just the change of its coefficient. But here it's going to be slightly different because we are linking the response to this linear combination. And again, what we're dealing with in Poisson is the log of lambda, or the log of the average. So if we increase one of our predictors by, say, 1, log lambda changes by the coefficient. But that's a little bit harder to understand. Remember, what we had to do is we just took the exponential of each one of these and it became a multiplicative change. So a multiplicative increase or decrease depending on how we were compared to the value of 1. So if we were greater than 1, we're going to see a multiplicative increase. If it's less than 1, we're going to see a decrease. And if it's 1 exactly, well, then it doesn't really matter because basically it's multiplying by 1 doesn't change anything. Okay, so now what we've done is using the Wald test, we've looked at those coefficients and basically did the hypothesis test, which was stating does this predictor add anything to our model? So does the population parameter that beta sub, we'll say I, is that equal to 0 versus the alternative it's not equal to 0? But the question now becomes, well, what happens if we have more things? More things that we want to test at once, because for us doing the Wald test again, we look at each individual predictor, and we can remove one at a time. And as soon as we remove one, the model's going to change. But what happens if we wanted to remove many simultaneously? And we looked at this the last time around. That was with dealing with a partial F test. So we're going to do the same thing, except this time what we're going to do is called a drop in deviance. Now, we already kind of talked about what deviance was. This is kind of like how good our fit of the model is. The lower the deviance, the better off we are doing. So yeah, we're going to use this as our standard for being able to determine this. All right, here we go. So a drop in deviance compares the deviance between two models. So we're going to have one model which we're going to call the reduced model or the nested model, depending on what book or what online resources you're doing. So this is going to be the smaller model, and there's going to be a full model with all of the predictors in there. So if I have 5 predictors and I want to test a model that only has 3 predictors, or if I'm looking to add a couple more on, again, the one with the more is the full, the one with the less is the reduced, but the less always has to fit into the full. So that's the big thing there. So a large drop in deviance. So again, a better deviance means the model is better at being able to explain the variation in the response. So a large drop in deviance suggests that the predictors add to the full model, and they help explain the data better. So adding on those additional predictors do in fact help, but they help at a statistically significant level. It's not just adding them on and we're noticing something is happening here. It's they are actually making a difference. That's why we have to run this test. All right, so the drop in deviance test, as I said, compares the deviance between the full and reduced model. So we have a full model. Whoops, full. Where is my? There we go, pen. Yep. So we have the full model. We have the reduced model. So we generate these models. We find out, well, what is the deviance between the two? So we look at the deviance of the reduced, the deviance of the full. We take the difference of the two, and this is what is our drop in deviance. As I said, the D reduced, that is the deviance of the model or the nested model, so the one with the lower number of predictor variables, but all of those predictor variables are inside the full model. All right. So this is a hypothesis test. Again, we have to make sure that that drop is statistically significant. So our null hypothesis is the simpler model. The nested or reduced model provides adequate fit to the data. So there's more than enough in there already. We don't need to add any of these extra bits on. The alternative is the full model. provides significantly better fit. So in this case, we make the hypothesis is that adding on these additional things aren't actually contributing to the model. The alternative of this, once we see a large enough drop in deviance, we reject that null hypothesis, we accept the alternative, and the alternative is saying no, adding on those additional ones is in fact helping the model. All right. So again, assuming the null hypothesis is correct, the drop in deviance follows a chi-squared distribution with degrees of freedom equal to the difference in the number of predictor variables. So if I have my full model being 4 and I have a reduced model, I'm only checking 2 of those predictor variables, so the difference would be 2. I would have a degree of freedom of 2. All right, so for exercise 5, we want to perform a drop in deviance test. The full model is the model with all 4 predictor variables that we created last time around. The reduced model, we're only going to use the predictor variables add spend and new content. All right, so let's jump over to R to be able to do this. So I've already created some of these models, but let's create them again. So I'm going to call this full model. That's going to be my variable name. Again, I'm using the GLM function to be able to create this, not the LM function, the GLM function, because we're using generalized linear models now. We're still saying the number of visits, so again, talking about the website traffic. This is explained by the advertising spent, day of the week, season, and new content. The family, again, this is following a Poisson distribution, and the data is coming from the data frame, which is cleverly called data. Okay, so let's run this. So we've created that model. I'm going to do the same thing, except I'm going to have a reduced model. This time around, the visits is going to be explained only by advertising spent and new content. Okay, so we have a full model now. We have a reduced model. So let's start doing some of these calculations manually, and then we're going to plug them into the formulas. And I'll show you an easier way of being able to do that to get exactly the same results. All right, so the first thing that we want to do is we want to calculate the deviance of each one and take the difference of the 2. So in order to do that, I can use, and we can see this in line 108, the deviance function. So I'm going to call the deviance function on the reduced model and on the full model and take the difference between the 2. And I'm going to store this difference in a variable called drop in deviance. Okay, so now I have the difference in the deviance, but I also need to know, well, what are my degrees of freedom? Now, I know my full model is 4, my reduced model is 2, so thus it is only 2. But let's say I was trying to automate this in some way. So if I use df.residual, that is going to get me my degrees of freedom for my residual model. So I'm getting my input of this is the reduced model, the full model, taking the difference between the 2, and I'm going to store this in the variable name df_difference. All right, so we want to be able to find what is the probability, well, basically we're looking for that p-value. So if I have my distribution, as we normally would, I want to know, well, what is that right tail aspect of things? What is that, what is the, sorry, there we go. What is the probability? I'm just trying to look at the code here for a second and remember what I had written in there. So let's actually just break this down for a quick second. So what I'm going to do is I'm going to use this p, so that the prefix p is again for probability of a chi-squared distribution. I'm going to use the drop in deviance. So we're asking what is the probability that drop or deviance is less than based upon this degrees of freedom. So less than, so going to the left of that. Now remember, we don't want that. We want everything to the right. We want that extreme. So in order to get that other side of that, I can just take, well, what's 1 minus the opposite of that? So we're asking the question now, what is the probability that we see this specific drop in deviance or larger? So what is the probability that we see this or larger? So I'll write this on the screen. So what is the probability that we see DID for short, drop in deviance. I'm not writing this out properly. No, don't do that. What are you doing here? Stop. Eraser. Let's write this out a little bit there. So what's the probability that we see this greater than or equal to the drop in deviance? Again, this is assuming for a degree of freedom, so df is equal to 2. So what is the probability? If we ran this experiment over and over again, what's the probability that we would get this specific or larger drop in deviance if, again, that null hypothesis was true, and that null hypothesis is stating the fact that the reduced model is adequate enough? So if this is, again, the probability of us seeing this is less than alpha, where alpha, if not overly stated, is 0.05. So if it's smaller than that, because again, what we're doing is my distribution, I'm looking for that last little tail. So where am I in that tail? If this is my alpha cutoff point, where this is my 5% of the tail, am I falling to the right of that, which means my likelihood of seeing this is even less than that 5%. My 5% is my threshold. I'm saying if it's even less than 5%, well then, yeah, no, definitely reject the null hypothesis. Sorry, that was a little long-winded explanation of that. So the first part, the p-chi squared, that's just giving us the probability to the left. The 1 minus is asking us, well, what is it to the right of that? I'm going to store this in the variable p underscore value underscore drop underscore deviance. And let's print this to the screen. So it's telling me that the drop in deviance is 0.549172, or 54.91%. So again, if we ran this experiment over and over and over, and we saw this drop in deviance, and what is the drop in deviance here? Let's actually just print this to the screen. So if I run just this line here, my drop in deviance is only 1.19. So that's not even a major drop. So dropping those two, or adding those two variables on. Now remember also, let's do this for a second, just as a quick reminder. So if I do summary and full let's do full model. Remember, only advertising spent and new content were statistically significant in terms of our hypothesis test, or the Wald test. The day of the weekend, or the day of the week, and the season weren't statistically significant, actually had fairly high p-values. So are they actually adding anything to the model? Well, I know I can reduce, or I can remove one at a time, but basically what we're asking here is, can I remove them both? And what this is telling me is that the difference between my reduced model, so the one with only 2 of those predictor variables, and my full model, well, adding those 2 extra predictor variables doesn't reduce my deviance to a large enough degree. Again, as I said, it's only right here. It's dropping only 1.19885, so not even a huge drop there. There we go. So not even a huge drop. So again, if we ran this experiment over and over and over again, we would likely see this drop happen almost 55% of the time. So it's highly likely that we would see something along these lines. So that's indicating, or giving us more weight to the null hypothesis, or failing to reject the null hypothesis, which is exactly where we're at right now. So basically what this is telling us is adding on those 2 predictor variables is not increasing the benefit of the model in itself, or the explanation power or explanatory power of the model in itself. So therefore, we shouldn't add it on. We should fail to reject the null hypothesis, which again is exactly what we saw from the summary table. Well, almost. Again, want to keep emphasizing this part. For the summary table, this is per individual predictor variables. This drop in deviance, we're testing, can we remove these things simultaneously? And the answer to that is, well, yes, we can. So our hypothesis test, let me just write this out in here. Reduced model is okay versus the alternative, which is full model. I'll write it out a little bit better than that, go with what we have in the slides there, but just as a quick sort of in there. And so our p-value, 0.54, which is greater than alpha, so we fail to reject. There we go. Awesome possum. Now, I did say that there was an easier way of being able to do that, so let's look at the easier way of being able to do that. So instead of actually manually calculating what the drop in deviance is, or the difference in the deviance from the reduced to the full and your degrees of freedom, we can simply just use the ANOVA function. So using the ANOVA function, and we've done this beforehand, all we're doing is for our first input, putting in the reduced model, for the second input, the full model, and now we are just specifying the fact that this is going by a chi-square distribution. So we use the ANOVA again when we were doing a partial F test. We didn't specify the test because it's by default for the partial F test, but now we want to specify that this is in terms of the chi-squared. So again, same result, different test, or same application, different test. Can we drop multiple things, or if we're adding multiple things, is it beneficial to do so? And so if I run this, I should get exactly that same thing of 0.5491272. And with a little bit of rounding, notice down here in the output, so we have the degrees of freedom for the full model, for the reduced model, the deviance for each one, the drop in deviance, the degrees of freedom, and what is the probability? Well, that's the 0.5491 rounded to 4 decimal places. So that's exactly what we get. We get the same outcome regardless. So we don't need to calculate all of these by hand. We can simply just use the ANOVA function exactly like we did in the partial F test. Okay. Let's jump back here. Where is my mouse? There we go. So just a couple of things to note here. So in terms of the drop in deviance versus the wall test. So the drop in deviance and the wall test usually provide constant or consistent results. However, if there is a discrepancy, we stick with the drop in deviance. That's typically the preferred way. But typically for what we've seen, they're going to come out with exactly the same results. So not only does the drop in deviance test perform better in most cases, it's also more flexible. That's kind of the key point there. So if two models differ by more than one term, then the drop in deviance tests essentially test if a single coefficient is 0 or not. So it's basically doing exactly the same thing as the wall test does. While if the two models differ by more than one term, then the wall test is no longer applicable. As I said, when we're doing that wall test, we're looking at each individual predictor variable. Here we're looking for a subset of them. So if we're doing a drop in deviance test with respect to only one variable, they should be working in exactly the same way. All right, so the last thing that we're going to be talking about here, the last thing that we're going to be talking about is lack of fit and how do we deal with this. So there's several reasons why we have lack of fit. So one is we may be missing important covariance or interactions, or a more comprehensive data set may be needed. There may be extreme observations that may cause the deviance to be larger than expected. And lastly, there might be a problem with the Poisson model. So we are going to be looking at this. Do I have this in here? Actually, give me 2 seconds. Let me go back through my R code here because I believe I talked about this not too long ago. Yeah, again, when we were talking about overdispersion right at the very beginning, I was just going through the code. I'm like, I remember us talking about this. It wasn't that long ago. Yeah, so we did a goodness of fit test, and that was basically just testing whether or not the model was a good fit. That was the null hypothesis. The alternative is it's not a good fit, and usually overdispersion of that. So what happens? Now we're going to be talking about that lack of good fit. So again, there's a couple of reasons, as I just said. The first two are the standard ones here, but also at the same point in time, we've made the assumption that this follows a Poisson distribution, or the random variable, the random component part of this, the response follows a Poisson distribution, where that might be somewhat-ish true, but there is some level of constraint that is happening in there. So the Poisson model has only a single parameter, that is the lambda. So if we remember this from our first stat course, the 2601, the 2507, or something along those lines, then the mean has to equal the variance. And again, that's our lambda there. Now, this might not be true. So the limitations become or can become manifest when the variance appears to be larger than the corresponding means. So in that case, the response is more variable than the Poisson model implies, and the response is considered to be over-dispersed. So when we violate that assumption of the same mean as the variance, then what we have is over-dispersion. Oops. Back to my other screen here. So just a little bit about overdispersion. So overdispersion suggests that there is more variation in the response than the model implies. Again, lambda is equal, or the mean is equal to the variance. So under a Poisson model, we would expect that the mean and variance of the response to be about the same in various groups. So if we grouped our data together, now this might be by age range or something along those lines, and we looked at, okay, for this group, what is the mean, what is the variance? That should be the same. Let's go up to another age group in here or something along those lines. So if we jump by every 5 years, we go up to another age group, we calculate its mean and variance. Is it roughly the same? Now, these two groups don't have to be the same. If the mean grows, the variance is going to grow. If the mean shrinks, the variance shrinks. But again, we need to be able to see how this behaves over the span of the data that we have. So without adjusting for overdispersions, we can use incorrect, artificially small standard error. So think about this. It's the same sort of thing when we were talking about that multicollinearity. What we're going to do is, unfortunately, we're going to overinflate. In this case, we're going to underinflate. We're going to overinflate the standard errors. So when we were doing the overinflation of the standard errors, that decreased our test statistic, but increased our p-values. Here, on the other hand, because we are artificially having an artificially small standard error, what this is going to do is it's going to overinflate our test statistic and underinflate our p-value, so making it look like they're a lot more statistically significant than they actually are. So again, we're not talking about being able to predict, but we are talking about the ability to explain what is happening based upon the coefficients of the model. So how do we deal with this? Well, there's two ways of being able to deal with this that are slightly different from one another. So we can create a new model, which is going to be a quasi-Poisson model. Now, what this does is it's going to reinflate that standard error. So we had a smaller standard error. This is going to enlarge that standard error by some scaling factor, which is then going to go and change up the test statistic and the p-value. So when we're running the hypothesis test, we'll have more accurate test statistics to be able to compare to. Now, what this does not do is it does not change the estimates that the model came up with. Now, the second option is we can create a new model, which is going to be a negative binomial. So we're going to use a different type of distribution here. So no longer a Poisson, but we're going to be using a negative binomial. This will, in fact, create new estimates for us. And it's going to give us new standard errors, so on and so forth. So the quasi-Poisson is just kind of reinflating that standard error, keeping everything else the same. The negative binomial is actually creating a new model here. So in terms of the quasi-Poisson, we can take overdispersion into account in several different ways. The simplest is to use an estimated dispersion factor to inflate the standard error. So how do we do this? This is kind of our scaling factor here. So we have this phi, which is just simply the sum of the squared residual or Pearson residuals divided by the degrees of freedom, which is the rate of the model's deviance to the degrees of freedom. So what we do is we take the original standard error that we have, and we're just going to multiply this by the square root of this inflation factor that we have. So one thing to note, this does not change our estimates, as I said before, but will change their level of significance, because if this changes the standard error, this is going to change our test statistic, which is going to change our p-value, which may or may not change our hypothesis test. Now, the negative binomial is different. This is a little bit more complex. I'm not going to get into the ins and outs of this, but just give you the kind of general overview of this. So the negative binomial model can accounts for the overdispersion by adding a dispersion parameter to this, allowing the variance to be greater than the mean. So we're adding on an additional parameter to allow us to do it. So we're not just taking the standard error and scaling that anymore or reinflating it. We're adding on a new additional parameter to this. So this improves the model fit when the Poisson assumption of equal mean and variance is violated. So what we can do is we're going to calculate variance in this slightly different way here. So originally beforehand, the variance was simply just equal to what lambda sub I is, mean is equal to the variance. But now what we're doing is we're adding on this extra parameter here where we're going to take, well, what is our mean? We're going to square that and we're going to divide it out by this new dispersion parameter that we have. Now I'm not going to go into how we calculate the dispersion parameter. R is going to do that for us. But even then, so once we specify which model we're going to be using, we don't even need to really deal with this, but just understand the fact that what we're doing here to create this is we are adding on an additional parameter. We did not have this before with the quasi-Poisson because all we're doing is just scaling the standard error that we have beforehand. Here we're actually changing our variance by adding on this extra parameter. All right, so for exercise 6 now, what we want to do is we want to fit a quasi-Poisson and a negative binomial model to handle the over-dispersion. Now we want to ask the question, is there a difference in the models, why or why not? Now we can kind of jump to the answer to this already because if we remember back, we already did a goodness of fit test. And the goodness of fit test, we failed to reject the null hypothesis. The model was already good enough. So when we looked at that difference between, well, what are our degrees of freedom? What is our residual deviance? If this is relatively close to 1, again, we are good with this. How close do we need to be? Well, we run the hypothesis test, and in this case, we failed to reject, which meant, again, that null hypothesis, the model is relatively a good fit. Okay. So if the model is already a good fit, we don't really have an issue with over dispersion. So what we would expect to see when we create these two new models, they should be very, very similar to the original model. Now the negative binomial obviously will change a little bit because we add in that dispersion parameter. The mean and variance is not perfectly equal, so we'll see some change in there. And again, same idea with the quasi-Poisson. We should see a slight change in there as well, but that dispersion parameter is going to be very, very close to 1. So the square root of 1 is still 1. Multiplying something by 1 isn't going to change anything, so the standard error should be very, very close. All right, so let's jump over to R and let's actually do these calculations. So the first thing that we're going to do is we are going to create the quasi-Poisson model. So how do we do that? We're still using the GLM function, and we're still talking about the full model, not the reduced model. So I was still saying visits is explained by advertising spent, day of the week, season, and new content. The family this time is not Poisson, it's quasi-Poisson, and data is still coming from exactly the same thing. So let's run this. Let's run our summary, which comes right afterwards. And I'm going to add in here summary, and let's look at full model. Because really we want to see the difference between these two things. So what's at the very bottom should be the full model. What is above that is going to be for the quasi-Poisson. Now notice in terms of the estimates, I have 1.49 e to the 0, 1.51 e to the negative 2. If I'm going down here, 1.496 e to the 0, 1.501. Can I put these all on the same screen? Yeah, these are exactly the same, but they're supposed to be the same. Our estimates should not change. Now notice for the quasi-Poisson, the dispersion parameter, very close to 1, 0.91728888. So we will see a slight change in our standard error. So standard error goes from 2.503 e to the negative 3 to 2.398 e to the negative 3. So it is going to change. It does change our t-values, and it does change our p-values. Slight changes, not massive changes, but that's, again, what we expect to see. Now notice, again, in the full model, we put this as a Poisson, so the over-dispersion parameter is automatically set to 1. So we're assuming that it's not in there, but there could potentially be something in there. All right, now let's do exactly the same thing, but with a negative binomial. Negative binomial. So this is on line, at least for me, line 126. So again, we are using the GLM, but not only the GLM, we're using the GLM.NB for the negative binomial. We're saying visits is explained by advertising spent, day of the week, season, new content, and we're doing data is equal to data again. So we don't have to specify the family in there because, again, that's done with the glm.nb. We're telling it that it's for a negative binomial. So if I run this, and I run the summary of this, and again, let's run the summary of the full. Our estimates, come on. So 1.49 e to the 0, 1.49 e to the 0, exactly the same. 1.501, 1.500, got very small difference there. 8.916, that is for day of the weekend. Here it's 6.863 e to the negative 4, but they're both e to the negative 4, so again, shifting that decimal spot over 4 spots. Again, these are incredibly small numbers to begin with, so even though it looks like there's a big change in there, because of this, the decimal representation of that, it's actually really small. New content was the only other one that was significant. That was 3.002 e to the negative 1. 3.002 e to the negative 1. So when things are really statistically significant, they don't really change. When they're not statistically significant, there's minor changes that happen inside of there. Standard errors, 2.727 e to the negative 3. This is 2.503. So again, we're not seeing massive changes, but we wouldn't expect to see massive changes in this case because we don't have major violations of things that are happening here. The models will be slightly different. We expect them to be slightly different, but they're only slightly different because, again, it's not perfect. The mean and the variance is not perfectly equal to one another, but it's very, very close. But a key thing to note here, again, is really the fact that, what do I want to say? The coefficients, or those estimates for the coefficients, are exactly the same when we're talking about a Poisson and quasi-Poisson, but it is going to be different when we're talking about a Poisson and a negative binomial. There we go. Oops, got to change up my screen here. I'll go over here, and we're almost there, which is not too shabby. We're just over half an hour here today, so it might be a little bit of a smaller lesson. The last couple of lessons are always usually smaller, which is nice. All right, so last thing that we want to be able to talk about. So we've already talked about how we interpret the model, how we create the model. If the assumption of mean and variance being equal to one another doesn't hold true, that's over dispersion. How do we deal with that? The last thing that we want to talk about is the offset parameter. So the offset parameter is used when there is what we're going to call an exposure variable. So this could be the population size or time. We want to be able to have things following that same time frame. So if I was comparing things, I want to be able to compare apples to apples. So if I'm comparing the size of of events happening at a university campus, well, I want to make sure that if I'm talking about the number of things happening in a given period of time, I'm reflecting the size difference of these. If they're exactly the same in terms of size, okay, no problem there. But I could have a much larger university to a much smaller university. Thus, if I'm seeing a massive increase in something happening at the smaller, this should have much more weight than it happening at, or a small change in the larger. All right. So an offset is a term in the model that adjusts the exposure without estimating its coefficient. So for example, in the US, so basically what I mean by that is it's not part of the model itself. There's no coefficient that is assigned to this offset. It's just something that we either add to it based upon, or add or subtract based upon the information that we'll provide. But you'll see that in just a second there. All right. So for example, we're going to use the US arrest data set. So we're going to use urban pop as the offset to account for population differences. So again, the offset term works by adjusting the predicted count based on the exposure variable. So in this case, that's going to be population size. If we're comparing things, we want, again, the number of times something happens, we want to take population size into account. Again, without estimating a coefficient for it. And what we see in the model here, so what we had beforehand is our log lambda is equal to our beta naught, beta 1x, all the way up to beta p xp. Notice the betas are those coefficients, but now I have an exposure variable here, something that I'm adding to it, but I have no coefficient to this, and that's what we want to have, is no coefficient to this. So included in the model, the offset term changes the linear predictor to exactly what I have down here. where exposure is the variable we want to adjust. And again, in this case, it's urban population. So first things first, let's jump back over to R and let's look at this data set before I start playing around with it. So line 132, at least for me, I'm just using the data function and US arrest is going in here. Now let's pull in US arrests. All right, so we have different states in here, and for each one of these states, it's recorded the number of murders, assaults, urban population, and rape cases. Okay. So again, an increase in any one of these, we definitely need to be taking into account the population. If we're seeing murder increase drastically or be very high in an area that has a very small population, this should be a great concern. Whereas if we have something that's relatively high, but we have a massive population, well, with respect to that population, it might actually not be all that much. So we want to definitely take these things into consideration. So in this case, what we're looking at is that urban population. That is our exposure variable here. Okay. Why do I keep losing my mouse? Here we go. Too many monitors. So the first thing that we're going to do is we are going to create two Poisson regression models, one with an offset and one without, and we are going to compare the two. All right, so back into R, I've brought in the data set. So the first model I'm going to create is model with no offsets for the US arrests. So how do we do this? Again, we're just using that GLM function. Assault, which is what we're trying to predict here, is explained by murder, rape, and we're not including the urban population. Now, the family of this is Poisson. Data set is coming from the US data sets. Now I'm going to create one with an offset. Now, how do we do this? Slight change. So again, GLM is still the function we're going to call. Assaults is explained by rape plus murder plus, murder plus rape plus offset. I'm using the offset function, and I'm going to do the log of urban population. So in terms of the model and how we're building this, it's exactly like the formula that we have. It's the log of whatever that offset is, and that's what I'm adding onto the model. Now I'm using the offset function to make sure that I am not calculating a coefficient for this. The family is still Poisson. The data is still coming from the US arrests. There we go. So let's run this one. Now let's compare the two models. So the first one is the one with no offset, and the other one is with an offset. All right, so with no offset, I have an estimate or an intercept of 4.14 and change. Murder has a coefficient of 0.069 and rape is 0.017. Now notice, in my offset model, I don't have an additional term. I don't have an estimate in there. Well, I don't want an estimate for this. My intercept is going to be different, and my coefficients are also going to be different here as well. But I don't have an offset parameter. But we can see when we do the call, offset is in fact included in here. All right, does it really help anything? Well, I have a residual deviance and degrees of freedom, residual deviance, degrees of freedom. So these things, well, the degrees of freedom don't change, but the residual deviance here does change a little bit. So because it's giving us a different model, it's going to give us a different deviance. All right, so let's talk about this here for a second. How the offset works in the predict function. So when you include an offset term in the Poisson regression model, the offset is part of the linear predictor during both model fitting and prediction. So we did see that. We did see that it became a factor when we were actually doing the prediction of the coefficients, different coefficients. But we haven't seen it in terms of the predict. We're going to do that now. So the offset is used during the model fitting to adjust the coefficients to account for the exposure variable. So again, how often is something happening, in this case, the urban population? When making predictions, using the predict function, R automatically uses the offset that was included in the model. right, so for exercise 8, we are looking to predict 2 new outcomes. So let's suppose we have murder of being 5 and 10. So we're going to do 2 different cases. Rape is going to be 30 and 25. Now we're going to set urban population. For the first count, when murder is 5 and rape is 30, the urban population will be 300. And then when it's 10 and 25, the urban population will be 400. So we're going to predict the 2 outcomes using the predict function, and we're also going to do this manually. All right, jumping back over to R. So using the predict function, remember, I need to create a data frame where each data frame or each row of that data frame is the entries for my model. So I have my model, which is the assaults is explained by the murder and rape. So I need information for the murder and rape to be able to put in there, but I also need an urban population because I'm doing an offset here. Okay, so I'm going to create the data frame using the data frame function. My first column, this will be for murder, so again 5 and 10, rape 30 and 25, and urban population 300 and 400. Oops, actually, let's remember to create the data frame here. There we go. Now using the predict function, I'm using model offset underscore US arrest. My new data is coming from this new underscore data set that we just created, and type is equal to response. So one of the things that we need to have here is response needs to be put in there. You'll see why in just a second. So let's do this, and we've stored these to predict assaults new, and we've done that. So the first one predicted at 596, the other one predicted at 1,177 and change. All right, let's do this manually now. So what I'm doing here is I'm asking for the coefficient for model offset arrest in the first position. So I'm asking for the intercept. Then I'm asking for the second coefficient times the new data coming from the murder column. And then the third coefficient, and then I'm taking the rape information. So basically what I'm doing here is it's like I have y is equal to my intercept plus some coefficient times the variable plus some coefficient times the variable. I'm creating this manually here, and I'm just taking exactly what my coefficients are from the models that were created, and I'm using that new data frame as my input here. And now I'm adding on that log new data exposure. So I create those manually. But what this is going to give me is the log lambda of this, because that's exactly what I've created here. When I do everything additively exactly like we have in the model, that's giving me something for log lambda. Now, if I take e to both sides, what is this going to do? So I take the exponential of this. This is now going to get me lambda. And if I print this out, this gives me 5.968 or 5.96.8944, and again the 1,000 and change for the other one. So this gives me everything back in terms of lambda. Now what happens if I did, let's get rid of the type is equal to response. And I run this, and I predict this. Notice now my predicted for each one is 6.39 and 7.07. These are vastly different. Why are they different? Well, because these are for log lambda. And if again I run the original code here, and let's just print this out, linear, new predict, that's exactly what we get. So when we put type is equal to response, we get the predictor that we are looking for in terms of the variable. Not the log lambda, so not in terms of the link function of the original response in itself. So we did not need to do this beforehand because the link was the identity function when using the predict, but in this case that is not the outcome that we have anymore. Okay, so let's put this all back to where we were, type response, perfect. All right, so we created them manually now. Very last thing here for today. And then we're going to do a quick lesson afterwards, and this is going to be on the logistic regression. Probably going to be only one lesson on that one. It's going to be very, very similar to what we've just done here, but with a slightly different link function and a slightly different way of being able to interpret things, but the same sort of general look and feel of this. So in terms of the number of lessons left, actually, there's only about 3 lessons after this one. One for the logistic, and then 2 for the time series, and then that's it for the course. Yay! So kind of a conclusion here to wrap everything up. So in this lecture, we covered Poisson regression for count data modeling. So we created a data set to be able to do this. We looked at wall test for individual predictor significance, including manual calculations and comparison with the Z values from the model summary. We did a drop-in deviance test for comparing the nested models. We talked about over-dispersion, how we handle that using negative binomial or quasi-Poisson. And lastly, about the offset parameter. So again, if we're dealing with count data, and the big thing is how many times is something happening in a given time frame, well, again, we have to make sure that whatever we're bringing in, are those time frames exactly all the same? Is the population size exactly all the same? So on and so forth. So the offset allows us to be able to do that. So that puts us just over 46 minutes. So again, a little bit less than what it would normally be by just about 10 minutes. But there we go, an easier lesson for you. If you have any questions, comments, concerns, feel free to reach out. Otherwise, we'll see you back here next time.